When talking about thermochemistry, we'll often come across the word enthalpy. It has a very specific meaning, and we'll get to that, but it's a word that you've probably not come across before. It comes from two Greek words that, when combined, enthalpine means warm in. And it does have to do with heat and energy. Sometimes this energy causes molecules to get rearranged, like when a solid melts. Sometimes a chemical reaction will take place where bonds are broken and new bonds are formed. But sometimes energy just means that the temperature changes. Energy input doesn't always mean that there's going to be a rise in temperature. That energy can be used for some other things. Enthalpy itself is a combination of two different energies. The first energy, internal energy, symbolized with a U, is the energy of molecular structure. That means the energy that's stored in bonds, like nitrogen gas, N triple bond to an N, contains a lot of stored energy. You could think of it as potential energy, and molecular activity. So those nitrogen gas molecules bouncing around, kinetic energy. So your internal energy represents all the kinetic and potential energies of particles inside a system. So again, kinetic energy from the activity of the molecules bouncing around, and potential energy, the stored energy from the bonds between atoms. If the internal energy increases, often the molecules move faster, and there is a temperature increase. And it's likely because your molecular activity has increased. Your molecules are now moving faster. An increase of kinetic energy. If the internal energy increases, a phase change of the matter inside the system can also occur. That means that we might go from being ice to liquid water. We might go from a solid to a liquid. Internal energy is measured in joules. Capital J. So that's our internal energy piece of enthalpy. The rest comes from PV, boundary work. Boundary work is the work that the pressure and volume of a system puts on its surroundings just by being there. Boundary work increases as the volume of the system increases, or as the pressure of a system on its surroundings increases. Boundary work is measured in kilopascals times liters, which is also equal to joules. That brings us to enthalpy. It's a combination measurement. Enthalpy is the sum of the internal energy and the boundary work. Scientists cannot calculate an actual total enthalpy, or total H, for a system. They can only calculate changes in enthalpy when something happens to the system. Enthalpy is measured in joules. So here we have a system. In some container, maybe these are our nitrogen gas molecules moving around. PV represents the work on a system's container or boundary. U represents the internal energy of the system. Remember, that comes from the molecular structure of what's inside and the molecular activity. That's what U is. Everything outside of that container, everything outside that system is the surroundings. Take a closer look at the role of internal energy. If heat energy is added to the system of closed solid container of gas, the volume cannot change, and the pressure of the container on the surroundings does not change. The heat causes an increase in temperature. Of the gas inside. The boundary work change is 0. No change in volume. So the increase in enthalpy is equal to the increase in internal energy. If we look at our formula, enthalpy is equal to internal energy plus PV. So if PV doesn't change, the only thing that's changing is internal energy. If that increases, enthalpy increases. What that looks like is those little gas particles have started moving faster. Heat energy means their kinetic energy has increased. That means that these molecules are moving faster on average. Now let's look at the difference when we increase in our boundary work and internal energy. If a balloon with a flexible volume is heated, some of that energy is used to expand the volume by doing work against external pressure, and some will become internal energy, increasing the temperature. In both cases shown above, enthalpy increases. In the case of the balloon, internal energy increases by less because some of the heat energy changes the boundary work. Some of that heat that went in there went into pushing back against the volume of the container, expanding it slightly.